So we're talking about the contrapositive of the conditional statement, right? The contrapositive is the instance in which you switch the premise with the conclusion, but also negate it, right? So we'll start off with the inverse and the converse, because the converse and the inverse are not logically equivalent to in a given conditional sentence. So we got to understand under what circumstances they are, or they do have the same truth value. Right? So true, true, false, false, true, false, true, false. A nice, easy way to get your different possibilities for true and false for two statements or sentences, or phrases. Right? So you remember P stands for some statement. So does Q, and it's possible that P could be true and Q could also be true. It's possible that one of them could be true and the other could be false. It's possible that they both could be false. Right? So we want to account for all those things. It really doesn't matter what order you put these things in, as long as you've accounted for every possible pairing, right? Every arrangement of true and false if possible, right? So honestly, I'm not really 100% sure why I put the Q first, then the P. It's kind of weird. I'm going to call that a typo and change it here. All right. So that was weird. I don't know what happened there. But yeah, not P is simple because all you're doing is taking the value of P and negating it. You know, if it's true, make it false. If it's false, make it true. So that's going to be false, false, true, true. For not Q, it's the opposite of all the Q truth values, right? So originally it was true, false, true, false. So I'm going to reverse that, false, true, false, true. All right. So when I want to find P implies Q, so I'm looking at this one. That's not dealing with any of the not cases. It's going back to the original, but we will get to the not cases in a second. All right. So I'm looking at these two, and I'm looking to draw conclusions from that. All right. So from last class, you gotta remember or refer to your notes. The only instance in which a conditional sentence is false is if the premise is true and the conclusion is false. That's the instance where you broke your contract, right? You made an agreement and you didn't live up to it, right? So if I do all my homework, then I will pass the test, right? So you did all your homework, but you didn't pass the test, right? That's one instance where, you know, like you said, if I did all my homework, I'd pass the test, but I did all my homework and I didn't pass the test. You were wrong. You know, so that's the only instance in which a conditional sentence would ever be false, right? So we're looking at true, false, true, true. Right. So then the not P implies not Q. So this column here is referring to these two, using the same reasoning, right? The only instance in which a conditional sentence is false is if it's true implies false, right? So that's in the notes previously, but I'll write it again over here. So the only way a conditional sentence is false is true then false is equal to false. All right, that's the only instance. Every other arrangement is going to leave you with a true result. All right, so false implies false, true. False implies true, true. True implies false, false. True implies true is true. remember, I say implies, if then, they both mean the same thing. So if I say if false, then false, that's the same thing as saying false implies false. All right. So then we get to the biconditional. All right, this is trying to establish logical equivalence between these two relationships. All right, so when I'm looking at this one, I'm comparing it to the two that came before. All right, so now I'm looking at these two. All right, when it comes to the biconditional, the only way that they're going to be true is if both parts are the same. All right, biconditionals are true if both parts are true. Sorry, both parts are the same. All right. So if it's false, if and only if false, and the biconditional, we say it is if and only if, even though it sounds weird. All right. True if and only if true, false if and only if false, those would be true results. Any mixture of trues and false, those would give us a false result. All right. So true, false, false, true. All right. So this isn't a valid relationship because we don't have true all the way down. Right? It's not any kind of contradiction. It's just something that it's satisfiable. If it was false all the way down, we would say it's unsatisfiable. There's no instance in which it would ever be true. But there are some instances in which it's true. Right? So what we're looking at is a relationship between a conditional sentence and its inverse. Right? So when we're talking about an inverse, we're talking about negating the first part. So if I say, if I get, or I'm sorry, if I do my homework, then I'll pass the test. All right, I'll actually write that down. If I do my homework, then I will pass the test. All right, that's the P implies Q. All right, the not P implies not Q would be, oh, I don't want to put a comment in there. Where is it? Get out of here. So the not P implies not Q would be just negating each part of this sentence. If I do not do my homework, then I will not pass the test. All right, so that's what the inverse is saying. Now, it kind of feels like it would be true, or at least just as true as the original sentence, but it's not always true. All right, because it is possible for you to not do your homework, but still pass the test. Okay, so when we look at the truth value here, and I say, okay, going back to the P and Q, the instances in which it's true, you know, you get a true result over here where you do have logical equivalence would be the first case and the last case. So it's a little mind bendy, but basically what this is, it's really getting at is whether or not your original sentence was true or false, or your original components were true or false. So if it's a lie that I did my homework, then it's okay for it to be a lie that I will pass the test. Right? If it's true that I did my homework, then I would expect to pass the test. So everything would fall into place there. But it's not always guaranteed that you'll have logical equivalence. Right? Now, the next one is the converse. Converse is where you switch the two parts of the sentence, of a conditional sentence, the premise and the conclusion. Right? But a lot of it's the same. Right? We still get our P's and Q's. So true, true, false, false, true, false, true, false. P implies Q is the true, false, true, true. Now Q implies P, that's going the other way around. Right? That's going from the Q's to the P's. Right? So direction is important here because I'm saying go from the Q column to the P column, so basically read it backwards. I just want to have as much of this stuff on the screen as possible for as long as I can. So when I do that, I'm still using this idea that the only way a conditional sentence is false is if true implies false. Right? So this one is true implies true. So that's true. This one is false implies true because we're reading it backwards. Also true. This one is true implies false. Again, reading it backwards. That's false. And this one is false implies false. That's going to be true. And again, the whole idea behind the biconditional is looking for equivalence. Right? We're looking for any instance in which the truth values are the same. So I'm comparing these two columns to see what circumstances have equivalent. Oh, that's a little terrible. I'm just gonna leave it. The same truth value. Right. So true if and only if true is true. False if and only if true is false. True if and only if false is false. And true if and only if true is true. All right. So it's the same deal where it is satisfiable, but it's not, it's not by any means a valid argument, right, to say that the converse is true. Right? And this idea of the converse and inverse, when we tie this to geometry, it's going to come back in a big way. But with my sentence here, Q implies P would be if I pass the test, it's a little tricky with the tenses. I would probably say then I did my homework. Unless you're kind of looking at it as a general statement. If I pass tests, like just in general, I pass tests. I do it all the time. I pass tests. Then I generally do my homework. Right? That could be a way of thinking about it too. All right.
Can I ask a question? Sorry, I'm so sorry.
No, not a problem.
Is that last one the converse one?
That one was the converse, yeah.
Okay, thanks.
Yeah, no problem. All right, so the next one is the contrapositive. All right, so we're looking at a relationship between an original, some sort of original argument and the instance in which you switch and negate the components of that argument. Another instance where I think I don't know what I was doing with this table here, right? I think I got a little too cute with this because it's technically correct. It doesn't. I wanted to start with something a little simpler. Right, so let's see here. I'm just trying to think of the easiest way to fix it. All right, so I'm going to tuck in a little column here that we're going to call not P. Not perfect, but and then another adjustment. This should be P implies Q, and this should be not Q implies not P. That one, that was a disaster. All right, so the first truth table that we did was the inverse, a case involving the inverse. The second one was the converse, and now we're looking at the contrapositive. All right, and these are the corrections. Oh, actually, there's even more corrections. Because why wouldn't there be? So in that final column, it should be basically these two. I don't even know. I tried to highlighting that in white for some reason. These two should make up that last column. So this should be not Q. All right. So yeah, apologies for that. All right. So the setup is going to be the same though initially. True, true, false, false, true, false, true, false. That part should be okay. Let me go with a thicker marker. Oh, this is even better. I got an extra row and everything. I don't even know what I was thinking when I did this. Not pretty. Okay. Oof. All right. So we'll need to do the not Q and not P, but before we get there, might as well just tackle the P implies not P implies Q column. That focuses on the original column, pair of columns. All right. So anytime it's true implies false, the result is going to be false. Otherwise, it's true. So true, false, true, true. All right. So then I'm going to need the not Q values and not P values because I have to come up with this column, which is not Q implies not P. So I would need those components. Some people can do this stuff in their head, but it does take a little bit of experience to get there. Once you get comfortable with it, it gets a little easier to do, quickly and conveniently. But this isn't a course on logic; it's a course on geometry. So we're just, I don't want to say we're doing the bare minimum, but we're doing only the logic that is necessary in order to understand the geometry. Right? So yeah, like the level of experience that one would need to get in order to do this kind of stuff in their head, we're only going to spend like tonight on logic, and then we're going to be done with it. So you're not going to get that kind of experience unless you take a discrete math course or explore it further on your own. But we're looking at not Q as just being the opposite of the Q column. So false, true, false, true. And not P, obviously, by that same reasoning, would be the opposite of the P column. So false, false, true, true. So now I'm looking for not Q implies not P. right? And the only way, again, a conditional sentence would ever be false is if it's true implies false, right? So the first one is true, false implies false, so that's true. True implies false, that's our false case. False implies true, that's going to be true. True implies true, that's going to be true. Now, we pretty much established logical equivalence here because you can see the truth values are the same in these two columns. But go the distance, just using the biconditional rule, anytime the two truth values are the same, the result is true. Right? So true if and only if true is true. False if and only if false is also true. Then true, then true. So this is a valid argument. Also known as a tautology. This is previously indicated in the notes, but I didn't want to go flipping back and forth. My penmanship notwithstanding, tautology, Tautology, okay. So that's telling us that in every circumstance, in every possible instance with a conditional sentence, the contrapositive will have the same truth value. Okay. So if the original sentence, the original conditional sentence is true, the contrapositive will also be true. If the original sentence is false, the contrapositive will also be false. Not guaranteeing that they'll always be true, the conditional sentences, is just always guaranteed that the conditional and its contrapositive will always be equivalent, right? So my sentence above was, if I do my homework, then I will pass the test. The contrapositive of that would be, if I do not pass the test or did not pass the test, then I did not do the homework. Right? It feels correct. If I do my homework, then I will pass the test. So if somebody said, okay, so does that mean if I didn't pass the test that I must not have done my homework? Well, assuming the first one is true, then yeah. Right? No guarantee that the first one, the original sentence is true, because we all know of situations where you can pass a test without doing any homework. But yeah, if one's true, so is the other. One's false, so is the other. Right? If I fill up my tank with gas, I will drive 300 miles. Right? There's some circumstances in which that might not happen. Maybe your car breaks down. Right? But if you assume that one is dependent on the other, if I fill up my tank with gas, then I will drive 300 miles. Then if I did not drive 300 miles, then I must not have filled up my tank with gas. Right? Again, assuming one is true, the original sentence, the contrapositive would also be true. And tricky stuff, a little mind bending, but and really that's why, honestly, that's why contract lawyers exist. And try to close all these loopholes that come from the logic. All right. So, example. Let C represents Simone takes chorus, and S represents Simone takes Spanish. Using C and S and proper logical connectives, express each in symbolic form. If Simone takes chorus, then she cannot take Spanish, right? So that would be C implies not S. Maybe there's no room in her schedule for Spanish if she's taking chorus. Right? If she takes Spanish, then she cannot take chorus. All right. The second part of this is prove that the two statements are logically equivalent, or give a reason why they're not equivalent. I didn't give a whole ton of space here because in theory, this is your proof. We've already done it, except we use P's and Q's instead of C's and S's. It's the same general idea. What we have here is what's known as the law of contrapositives, right? They are logically equivalent by the law of contrapositives. Sorry. Right, and that's because if I take the C implies not S, switch it and negate it, I would get S implies not C. C implies not S, and S and not C are contrapositive. Right. The fact that you switch one and negate it and you get the other means that they're contrapositive. And we just established through a truth table that they're logically equivalent, creating creating a valid argument, which means that they're logically equivalent, right, in all cases. Right. So we have this law of contrapositives, but we also have other laws. Right. Law of double negation. Right. It's crazy how many typos there are. It's insane. I swear I edited this before the course began, and yet I keep finding typo after typo. This should have a not in front of the not. As in a double negation. Right. We also have De Morgan's laws, which is kind of a fun name, I guess, De Morgan. But it's basically telling us that if you have a disjunction and you negate it, it becomes a conjunction. Right? It's kind of strange, and you're really going to want to look at this as sort of like a reference table, because what you're getting with the biconditionals here is another form of equivalence. What these are really saying is that this expression is equivalent to this expression, right? That's what that biconditional is really telling us. What the laws of logic really boil down to is what we did here with this truth table, except we're not going to do a truth table for each one, right? So it's basically saying that if you created a truth table for each one of these situations, you would get true all the way down the last column, right? Creating a valid argument, creating a tautology, right? It wouldn't be something that's satisfiable or unsatisfiable. It'd be something that's satisfied in all cases, making it a valid argument, right? So in every situation, you look on the left side of the biconditional, you get one expression. Sometimes they're a little bit more complicated than other situations. And on the right side, you get what it's equivalent to.
Can I ask another question? What is the, when there's the parentheses or not the parentheses, is like, what is the purpose of number 3? I understand like how they're equal. I get that. But why would you put the parentheses in an argument or something?
So you wouldn't, it's kind of hard to really explain the need for parentheses because it doesn't really tie together with everyday language. But if you think of it in terms of grouping, like if I tell you that I am not, and I would never say parentheses, but I am not 30 years old and a science teacher, right? It's implied that those two ideas are grouped together, right? So I wouldn't say that I'm not open, if I'm writing a sentence in everyday language, I wouldn't say I am not open parentheses, 30 years old and a science teacher, But that's really what it's getting at, the idea that there's an implied grouping between two things.
Okay, and then the one that it goes with is saying you're not the first thing you said, or it's saying or the second thing.
Right, exactly.
Okay, thanks.
No problem. Yeah, I mean, some of them are more obvious, like the commutative laws. I mean, I think that's pretty okay, because if I tell you that I am going to wear a blue shirt or a red shirt, and then I say I'm going to wear a red shirt or a blue shirt, I'm really saying the same thing, right? There's no reason to think otherwise. Right? But then you get to the associative laws, and that's again, the parentheses is kind of weird. You start thinking about it like, man, what does that even mean? I am wearing either a blue shirt or a red shirt, or I'm just going to wear a jumpsuit. Like it's like the R in number 5, the associative law, that R is an alternative to the 2 other possibilities, right? So in the end, it doesn't really matter, because it's the associative law, it wouldn't make a difference. It's one or the other, but it just feels kind of like a weird thing. Right? But distributive laws, also kind of strange. If I say that I'm going to wear either a jumpsuit, well, I won't even throw the word either there. I'm going to wear a jumpsuit or a blue shirt and red shorts. Okay, what that would translate to is I am going to wear a jumpsuit or a blue shirt and a jumpsuit or blue shorts. All right, so in each case, I'm saying that it's the choice between the jumpsuit and the 2 other articles of clothing. Right? In the end, it's still going to boil down to a jumpsuit or those other possibilities, but it's still just kind of weird to think about. All right, the idempotent laws. Oh, spelling typo. Potent, not pontent. Jeez. And this didn't even get picked up. Well, maybe it did. Maybe I just ignored it. Idempotent. All right. So for that one, that's number 8. P or P is equivalent to P. That's your classic duh situation. Although the notation doesn't make it seem like it's an obvious thing. But when you think about it, it makes all the sense in the world. So I'm going to wear a blue shirt or a blue shirt. So I'm going to wear a blue shirt. I mean, those are my 2 choices. So I guess I'll just wear the blue shirt. Yeah. It's like when the teacher says, all right, you got 2 choices. You can either do the homework or you can do the homework. You're like, okay, you're funny, but I guess you're telling us to do the homework. That's the idea. So in every one of these cases, we're thinking of the biconditional as sort of like an equal sign. Right? So you get into the weird ones like the identity laws, just because those involve false and trues and things like that. But it's a nice way of pulling out a fact from something that doesn't necessarily involve complete information, right? So when we say P or false, that's equivalent to P, right? Well, that goes back to the general, or I'll even say the most basic rules. When we have the conjunction, I'll just rewrite them again over here. The conjunction, the only way you're going to get a true sentence is if it's true and true. For a disjunction, the only way it's going to be false is if it's false or false. Right? So conjunction, disjunction. Now, if I tell you, I'm just going to pull one of these out real quick. If I tell you, for example, that we have P or false, and the result has to be true, right? What that means is that there's no way that this can be false. Not possible to be false and have the entire sentence be true. All right, because we want this to be equal. We want this to, it's an identity. It's a law of logic. Laws are always true. All right, so this has to be a true sentence. The only way that that would happen is if the P, whatever P was true, right? So if I say, I am going to wear a red shirt or, and then I tell you something that's impossible. You know, I am going to wear a red shirt or I am a giant frog. Then you know that I'm wearing the red shirt, right? That's the thing that has to be true, because the other thing is it's got to be false. I mean, look at me, I look nothing like a giant frog, more like a salamander. So you have all these other rules. I could take you through every one of them, but you know, they are what they are. You know, you look at the expression. You kind of make a sentence to justify it in your mind, and then you kind of talk your way through it, and then you see how it goes. All right. But what I'll do is I'll show you by example, because we're going to get into some proofs, and what we want to do is justify an argument based off of the laws of logic. So in a lot of cases, you'll look at what's given to you and say, all right, what law is going to support this, right? That's really what it all comes down to. Now, there are some things where you see plenty of instances where it looks so weird that there's no way I'm going to be able to figure this out. But if you look at the key components like the and symbols, the or symbols, and things like that, and see what that corresponds to in our list, it gets a little bit easier, right? So I'm just trying to think, because some of these are a little. I want to start us off with something kind of easier, because I know from the past times that I talked, of course, I've always started off with something way too hard initially, and ended up having to backtrack anyway. So I'm looking for something that's quote unquote easy. So let me see here. Yeah, might have to go with one of these. Yeah. Let me, you know what? I know what I'll do. I'm going to make up a simple example, and then I'll just go into the other ones that I had originally planned to do. All right, so let me just create an example over on the side here. Something, again, I don't want to go too crazy too quickly. All right, so let's say we have P implies Q, and then we have not Q. Then we have, let's see here, not P implies R. All right, and we need to draw a conclusion from this. Yeah, that should be basic enough. It's still not going to be the most appealing thing in the world, but we'll call this our first example, first real example. All right, so what we're looking for is something that we could pull out of this table here, if we can call it a table, in order to draw a conclusion from this set of symbols that we have. All right, and you kind of get a little, and the word's not shell shocked, but intimidated, I guess is probably the right word, at least initially. But once you start looking at things carefully, you start to see things that go into, that start to make sense. Right? So what I want to do is take two of these sentences and put them together and see if there's a conclusion that can be drawn from. Right? So I'll start off with the first two. Right? The first two sentences here, P implies Q and not Q, right? I'm going to take those two and look at them in conjunction with one another, right? Whenever we're performing what we call a logic proof, we perform that proof by looking at multiple sentences in conjunction with one another, right? Because if we're going to determine truth value, all of these conditions need to be met, the first one and the second one and the third one, but we can only really look at them two at a time. So I'm going to start off with these two and say P implies Q and not Q. All right. So what I would be looking for is a rule that fits that mold. Now I use P's and Q's here for a reason, because that matches up nicely with what we have up here, right? So I would be looking, again, everything to the left of an if and only if is what you're starting with, and everything to the right is what it simplifies down to. So I'm looking for one that has a P implies Q and a not Q. And it doesn't take too long looking through the list before you realize number 18 is exactly that, right? P implies Q and not Q is equivalent to not P, right? So, I mean, you can throw some context into this if you want. If I do my homework, then I will pass the test. I did not do my homework. I'm sorry. I did not pass the test. That must mean I did not do my homework. Right. So my conclusion here would be not P. All right. So we were able to draw a small conclusion from this. We now know not P by the modus tollens law is a true sentence. All right, so that's our justification. We know not P is a true sentence based off of modus tollens. Right? So then, okay, well, now I know that P implies Q and not Q simplifies down to just a not P. I could throw a set of parentheses around the P implies Q just to give the appropriate grouping, because P implies Q was its own thing. Not Q is its own thing. I mean, I could put parentheses around that too, but that might be a little overkill. Right? But I've drawn a conclusion. This entire expression, or this set of expressions, really gets boiled down to that. Right? If I'm creating an argument and if I say to you, if you did not study, then you did not pass the test. Then I tell you that you did not pass the test. A good reply to that would be like, why don't you just say I didn't study? like you're trying to tell me I didn't study. Why don't you just say that? All right. That's really what this is getting at, trying to simplify it down to its most basic components. All right. So I can now take my not P implies R and put that in conjunction with the not P. And see what that's equivalent to. Can't really write. All right, now that one's a little trickier, only because there are too many instances in our table where we see an R. Right? But I do see one that involves a Q. Right? It has a similar structure, except instead of saying not P implies R and not P, it says P implies Q and P, but it has the same structure, right? Where the premise is repeated, right? So if I say, yeah, and so not P represents, my example, if I didn't do my homework, right? And so if I didn't do my homework, then I will be in trouble when I get home. I'm thinking of like an elementary school student. If I did not do my homework, then I will be in trouble when I get home. I can look at this whole argument by saying, if I do my homework, then I'll pass the test. I didn't pass the test. If I don't do my homework, then I'm grounded. So what does that mean? Like common sense tells you that you're probably grounded, but we want to confirm that. All right. So this is what we call modus ponens. It's affirmed by affirming. Right? If I tell you, if you don't do your homework, then you are grounded. And then I just found out that you didn't do your homework. Then that means you're grounded. Right? So that would tell us that this is R, it's equivalent to R, and that would be by modus ponens. Right? That's the affirms by affirming, or modus ponens is denies by denying. Yeah, that's a weirder one. I think the affirms by affirming makes more sense. But they're both logical laws, so they both work out. There's other names for them. The modus ponens is also known as the law of detachment. But honestly, you can kind of look at most of these laws as being some form of law of detachment, because you're breaking parts of an argument down into easier components to understand. But basically, just going through the scenario again, if I do my homework, then I pass the test. I didn't pass the test. If I don't do my homework, then I'm grounded. All of that simplifies down to one basic idea. I'm grounded, period. I could say it in 3 sentences, or I could say it in 1 sentence. I'm sure my son would rather I say it in 1 sentence. If he's going to get grounded anyway, he doesn't want the lecture. I'm one of those people that you either get the lecture or you get the punishment. So if you sit through the lecture, then you don't generally get punished. So it's a parenting style, but that's mine. That's how I operate. Operate is the word of the day. Operate. And so all you have to do is go into Blackboard, click on word of the day, type in operate, your name, operate, and use it in the sentence. Okay, so simplify, and we'll do this one example here, and then we'll take a little break. But simplify the following expression, given the reason for each simplification. All right. So, there's kind of a lot going on here, but if you can take some component out of this that makes sense, then you can draw a conclusion, and hopefully it'll be a simple conclusion. Because in theory, you don't want an argument to get more complicated when you apply the laws of logic to it. You want it to get simpler as you go, right? So the P implies Q, I can't really do anything with that, right? We know that there are circumstances in which P implies Q is true and a circumstance where it's false. It's really, the mess is over here. So we have not Q and R or not Q, all right? So I'm looking for a law. If I just focus in on this piece, I'm looking for a law of logic that's just going to deal with this part, all right? So I want an and an or in the same expression, right? So if I go back up to, I mean, we're in the neighborhood of associative laws, distributive laws, things like that. I'm in that neighborhood. I just got to find the one that matches, you know? So I'm looking for one that has a mixture of the and the or symbol. So I'm going to just kind of clean this up for a sec. Let me just pull this out, put it over here, because I want to grab those distributive laws and bring them on down so we can really dissect them. Screenshot. Yeah, it looks terrible. Bring it in. Okay. And then let me just put this stuff back. But yeah, I'm just going to bring this in over here and take a look. I keep hitting add a comment because they moved that function. Now it's frozen on me. Right, so these are the identity laws. And if you look at the second one, I'm sorry, distributive law. If you look at the second one, that seems to be the same structure as what, you know, what we're potentially interested in. Right, so we have not Q and R or not Q. All right. So that's, it looks like it's this one. Except we have to kind of match it to what we have. All right. So it looks like P is taking on the role of not Q in this law. All right. Q is taking on the, or R is taking on the role of Q, and not Q is taking on the role of R. You know, so it's kind of a lot of funky stuff going on here. But if we expand this out, we'll just do it kind of carefully and easily. So everywhere I see a P in my expansion, I'm going to replace that with a not Q. So that's here and here. Not Q, not Q. I have a Q here that corresponds with this Q. All right. So that's going to put my R here with an and symbol. We're going to go red. And then I have this not Q over here. That's taken on the role of R, so not Q. And that's another and. All right, so the argument seems to be getting worse, but it's about to get a little bit better. Right, if that makes any sense. And we'll see. All right, so this is a distributive law. All right, now not Q and not Q, that's the same thing. So if you go back to our laws, everything's accounted for in here. It's just a question of, you know, like what, you know, what's obvious. You know, sometimes you have something that may seem obvious at first, but then it really, you know, it really kind of isn't, you know. But anyway, so we can look at this. and say not Q and not Q, well, anything and itself is going to be itself. You know, it's just a question of what law do we have that's going to justify that, right? And sometimes it's just common sense, right? So if I tell you that I am wearing a blue shirt and a blue shirt, then it's pretty clear that I'm wearing a blue shirt, right? So this would just be not Q. So I have not Q and R, or not Q. All right. So we're still looking for a law that's going to help us clean this up. And you know, sometimes it takes a minute. Because you go down the list, you know, there's some things that are, you know, you're not going to be able to really do anything with. Like, I mean, we just used the, oh, it's not included here. This law that we just applied was the idempotent law. Yeah, that was the justification for this step. But yeah, we're just looking to see if there's anything that would apply. You know, we have the absorption law, perhaps. You know, we have P or P and Q. Right. So if we look at the absorption law, this one right here. Right. So you notice how in the parentheses you have a not Q, and then outside it's the same not Q. That follows the same model. So if I tell you that the result, you know, like whatever the statement is, trying to think, well, I guess I could use the grounded and homework stuff. So I did not pass the test and I am grounded, or I did not pass the test. So like, what kind of conclusion can you draw from that? You know, so the conclusion would be absorption, in that the result would be not an R value, just an R. All right, so absorption. And the rationale behind that is, if I'm looking at, again, a disjunction, so an or situation, I'm looking for true, some kind of truth value going on, right? So, oh, so sorry, I don't know why I put R there. It should have been not Q. Apologies. Yeah, so it's not Q because if in an or sentence I want to have a true result, I only need one part of it to be true. The other part can be false, right? So if I already know that not Q is true, then this not Q is also going to be true. It really doesn't matter what R is. R can be ambiguous. R can be true or false, because I've already satisfied in this disjunction, I satisfied the requirement of having one part of it be true. So if R is false, it still works out to be a true sentence. If R is true, it'll also work out to be a true sentence. It doesn't matter what R is. And what that actually means is that's actually not the best possible outcome if you're thinking about the logic of an argument, because that means that we can't determine the truth value of R. We can't determine whether it's true or false. By the way, you see at this point why I didn't lead off with this example. So we can determine the truth value of not Q if this sentence is going to be true, now Q has to be true, right? There's no other way it could play out, right? Because if R is true, let's say R is true and Q is false, then this whole component would be false. If this not Q is false, then this one has to also be false, making the entire sentence false, and we can't have that, right? So that's the justification for why the absorption law works. Most people are not overly interested in that. They're more interested in the fact that it does work. Right? It's like, it works, it's in the list, okay, good, fine, got it. Right, so now I have, and so I've been neglecting this P implies Q for the longest time. That's been there, I've just been ignoring it. But this is a tailor-made rule. This is going to give us a result of not P by modus tollens. All right, that was one of the ones that we let off with. The idea that if you have a conditional sentence, it's the denies by denying. If you have a conditional sentence, P implies Q, and you know the conclusion is false, then the premise is also going to be false. All right, so if I study or if I do my homework, then I will pass the test. I did not pass the test. Well, then I didn't do my homework. All right, so it turns out that that R was not material to the argument to begin with. Right? But depending on what R represents, you know, it might be important, it might not be important. Now, if I'm going with, again, P representing I do my homework, Q passing the test, and R representing being grounded, this is a very convoluted argument, right? Because it's saying, if I do my homework, then I pass the test, and I did not pass the test, or I do not pass the test, and either I get grounded or I did not pass the test. I mean, I don't know who would ever speak like that, but all of that would just simply mean that I did not do my homework. Right? But that's kind of an academic argument because nobody would ever speak that way, except if we were writing a contract or something. Right? So anyway, let's take a couple minutes because I know I would need a few minutes to absorb unintended this stuff. So let's pause, and then we'll come back in 5 minutes. So the methods to prove logical implications, that's basically what we've been talking about. And so I'll give you an example, or another example that has some context behind it. So it's a gated question, but Sam Darnold throws for 4,000 or more yards in 2020. Sam Darnold gets injured in 2020. The New York Jets win the Super Bowl in the 2020 season. All right. So those are P, Q, and R. Now, if I tell you that the premises are if Sam Darnold does not get injured in 2020, so getting injured is related to the Q statement. Then he will throw for 4,000 yards or more, right? So that's the P statement. So we're saying here that he did not get injured, so that's not Q. But we are saying that he'll throw for 4,000 yards, that's P. So since it's conditional, it's a sideways arrow, that's where this first sentence is coming from. Right? So then if Sam Darnold throws for 4,000 yards or more in 2020, so again, that's the P statement. The Jets will win the Super Bowl in the 2020 season. All right, so that's the R statement. So this is P implies R. That's where this one's coming from. Right? And then Sam Darnold does not get injured in 2020. So that goes back to the Q statement. He did not get injured, so that's not Q. Right? So what we're looking to do here is make or draw a conclusion. So we have the premises here, P1, P2, P3. It doesn't really matter what you call them. It's just, these are just premise 1, premise 2, premise 3. If they're all going to be true in conjunction, then it can only play out in a certain way based on the laws of logic. Right? So in order for this to work out, we would have to determine what would be the result of the simplification between not Q and P and P then, I'm sorry, not Q then P, and P then R and not Q. Right? But because of the commutative laws, we could do these in any order that we want. So it actually makes sense to focus on these two. Let me get a different highlighter color here. Oh, it's like baby blue here. So it makes sense to focus on these two first. Sometimes an arrow is just an arrow. So this is not Q then P and not Q. That's going to result in a P. Actually, these arrows look pretty terrible, so. Not much better. All right, but that result is going to be P by modus ponens. All right, that's the affirms by affirming. All right, so we've confirmed the premise, so the conclusion is true. Right? Because if the premise is true and the whole sentence is true, then the conclusion also has to be true. Because you're just going back to the implication and what would cause an implication to be false. That's true implies false. So if I were to tell you that the not Q was false, then that would be okay, I guess, as long as not Q implies P wasn't true. If that ends up being true, then you get a problem, right? I'm sorry, if the not Q, well, actually, I apologize. I was looking at this as if it were a conditional. If the not Q is false, then everything's fine because it doesn't matter what Q is. Right? But if the not, sorry. Oh, sorry, that was a question. If not Q is true, then it matters what P is, because then if P is false, then the whole sentence would be false, and that would be a problem. But we only want true sentences, right? So that forces P to actually be true, right? And the law that justifies that is modus ponens. Now, what a lot of people will say is, okay, that explanation, that really wonderful convoluted explanation, that's great. You're telling me that if I have a conditional and these two things match, then the answer is P. And the reason for that is modus ponens. All right, that's fine. I can live with that for now. Yeah. But now we have a conclusion. We know that P is true. That's a true sentence. Right? So we now know that Sam Darnold threw for 4,000 yards or more in 2020. Actually, I have no idea. I'm not a Jets fan. I don't know why I use San. But I have not accounted for this component yet. So what I can do now is take this and put it in conjunction with the P and draw a conclusion from that. Also affirms by affirming. Again, it's you have a conditional, and these two things are the same, then the result is going to be whatever the conclusion of your conditional is. Okay? So in this case, it's R, which means the Jets won the Super Bowl. And again, by modus ponens. Right? And so that's the justification for why we can say all this. You know, because the logical conclusion by modus ponens is R. Maybe this is my subtle way of torturing Jets. Like, yeah, they won the Super Bowl in 2020. No, they didn't. No, they didn't. 1969. So anyway, if you're ever in trouble and you can't figure out a law to justify an argument, you could always create a truth table. Right? It's just not going to be pretty most of the time, especially when you have all these different components. Right? So what you'd have to do is actually create a truth table using all of this. Right? So the ideal way of handling it is to use the laws of logic to draw the conclusion, but then, you know, if you're jammed up and you really can't figure something out, then your emergency situation break open glass is to create a truth table. Right? So we'll do it. You know, I think I need to expand this table though, because again, I don't know what I was thinking. Right? So we have P, Q, and R. These are all the different ways that you could have three statements be either true or false. All the different arrangements of true and false for three statements. Right? They could all be true. They could all be false, and it could be any other combination, any other arrangement. I should say. So I have a not Q implies P, a P implies R, a not Q. Okay, so that's telling me that I think I need a not Q column. Let me do that. Right, so false, true, false, true, false, true, false, true. Then I need the Q implies P. I'm sorry, not Q implies P. And then I'll need like 7 more columns after this, but one thing at a time. Right, so not Q implies P. Let me just focus on the right columns here. Here's the P column. Here's the not Q column. Right, and we're going in this direction. So if it's true implies false, it's false, otherwise it's true. So I got true, 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 this one's false, true, 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 and this one's false. All right, so now like I said, I just need more rows and more columns. Bear with me for a sec here. All right, so next up would be P implies R. You know, let me do that in blue. All right. So that would be these two columns. Oops, that's pretty obvious. And I forgot to highlight this one in green, so let me do that. All right, so the P implies R. Again, true implies false is false, otherwise it's true. So true, 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 true. This one's false. This one's false. True and true. All right, so now I need conjunctions with these three components. All right, so that part's not too bad because, and we've only talked about conjunctions as it applies to two parts or two pieces, but in order for any conjunction sentence to be true, all parts have to be true. Right, so that kind of simplifies things a little bit. Right, and the only way a disjunction sentence is false is if all parts are false. Right, so when I'm looking at not Q implies P and P implies R and not Q, I'm just going to look at the respective columns and just verify or determine instances in which all parts are true. But those are the only instances in which the sentence will be true. All right, so I just need to know what columns I'm looking at. So it's essentially, commutative property is really helpful here. It's these three columns here. I'll actually get this one involved too. All right. So I'm only accounting for any instance in which all parts are true. So this one would be false. This one's true. False, 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 more false, lots of false. Really, there's the only instance of which it's true. Right? But then all of that now has to imply the R value. And that's where we're going to get our tautology. All right, so we'd be looking at all of this stuff that I wrote already, a whole lot of it. Not Q implies P, and P implies R, and not Q all implies R. So clearly we don't want to have to do this too many times. That's why I'm saying it's a emergency situation. I just can't figure out what laws I'm supposed to use. So let me make a truth table. Right. So it's basically saying, take, I'll get a different color here. I'll go back to purple. Take this column here and have it imply, and my arcs are getting a little crazy here, so I'm gonna move that. And have it imply the R column. All right. There's never an instance between these two columns where you have true implies false. It's always false implies true, or false implies something, or true implies true. So no matter what arrangement you have in those lists, it's true all the way down. but it is also reliant on the original premises being valid. All right, but basically this is saying, my premises were if Sam Darnold does not get injured in 2020, he'll throw for 4,000 yards or more. If he throws for 4,000 yards or more, the Jets will win the Super Bowl. And that Sam Darnold does not get injured in 2020. So in theory, that means that he threw for 4,000 yards or more, and that caused the Jets to win the Super Bowl. Right? But there's other variables at work. But if we've accounted for every possible variable and come up with a tautology, then it's a guaranteed event. Right? But obviously, we didn't account for every variable because the Jets didn't win this. Fun. All right, so you're comparing what we wrote here with what we wrote here. Aside from it just being motivation to get a decent handle on the laws of logic so that you don't have to create the truth table, it's also a way of verifying that what we're doing is logically sound. All right. But yeah, I mean, if you have your rules handy, it really is just a matter of time. Right? Some of the examples on the next page involve more rules. So let me go back. I'm just going to copy and paste and bring them down so I can at least point to them.
Do we, like, when we work through these, can we reference the rules?
Yeah.
Okay.
Yeah, this is one of those situations where, I mean, I have like to think I have a pretty good handle on this material, but every now and then there will be a law that kind of slips my mind. So even I have to refer to the tables every now and again. There's some where you kind of look at it and say, okay, well that's obvious, or at least it will feel that way after a while, aside from typos, because the not P is that's the law of double negation. Like if I tell you I'm not gonna quit, those are two negative connotations. Right? So sometimes it's not as simple as saying I am not going to not do my homework. I mean, most people don't speak that way. But if you throw a not in front of something that already has a negative connotation, then that's where the law of double negations apply. Like, I am not, knock on wood, I am not going to die. The die part is the negative, right? So not die, live, so in terms of the language, you get at the simpler meaning, so just by removing the not. Right. So when we say prove something, it's justify it using a law of logic. Right. So prove Q implies P is logically equivalent to P or not Q. So I go down my list, right, just looking for something that has a similar structure to that. Right. So if you look at the very last one, it's the implication identity. Number 19. Now my highlighter's too thick. I copied and pasted, but it's a few pages earlier. P implies Q if and only if not P or Q. So this is the implication identity. We need a thicker marker. And if memory serves, we talked about this last time, but I could also very well be thinking of a different class. This would be the same as saying, if I do my homework, then I pass the test. That would be equivalent to saying, I do not do my homework, or I pass the test. And it kind of feels a little funky, but it also, the more you think about it, the more it sounds like it's probably correct, right? So now this isn't quite the same, but it's pretty close, right? So kind of look at it as, I say it as so-and-so is taking on the role of something, it's like the understudy. So here, Q is taking on the role of P, right? So I would ask myself, all right, well, what happened to P in this implication identity? All right, so let me go with a different color. Well, the P became a not P. So following the same relationship, Q should become a not Q. All right. P is taking on the role of Q. So what happened to Q? Q stayed put. So P will stay put. All right. So we have poor quality disjunction symbol. We have this relationship by the implication identity. All right. Pretty close. Right? One is the actual rule, but that's pretty close to what they're telling us. They said P or not Q. Right? Well, Q, not Q, or P is the same as P or not Q by the commutative law. All right, we could switch the order. All right, so that's the fourth rule up there. All right, so it's all we're really doing is getting what they say to fit a rule that we already know or have access to. Not always easy, but it's certainly easier than making it true. So number 2, prove P and not Q is logically equivalent to not P or Q. That's fun, right? When you're proving logical equivalence, I tend to want to work with the one that's more complicated because that's probably the one that you can simplify. But again, we're just looking for rules, right? So I see a double negative, maybe that'll come into play, but I also see that I'm negating something in parentheses that involves an or, right? So I'm looking at the De Morgan's laws. Right. So one version of the De Morgan's laws says right? It says that if you have a not P or Q, that's logically equivalent to not P and not Q. Right. So I'm going to look at my not P or Q. And I'm going to see what that translates to. Right. So here, the not P is taking on the role of P. So you think about what happened to P. It got negated. Negated as in its sign got reversed. Not it became negative. It changed signs. It went from positive to negative. But if it's negative, then it'll go to positive. right? I'm using negative as in like an algebraic sense, like a negative sign. Like what happens when you negate a negative? It becomes positive. That's the same thing that happens to a not symbol. It becomes a positive or a not. Right? So there's a hidden step in here in that what we're looking at, again, because it's a negation, the P became a not P. This is really becoming not P. We'll address that hidden step in a second. Right? And well, the Q, there's no change there because the Q is taking on the role of Q. Q becomes a not Q, so this Q would become a not Q. Right? So then the only thing I'd have to make or draw a conclusion on would be this, because that would be P, and that would be the law of double negation. Right. So De Morgan's law has got us the first step, and then there's a little half step in there. There's, like something could be common sense, like, oh, I'm going to negate the negative, but it's got to be an explicit proof. Right. So every little thing has to be justified. You can't just make an assumption. And as much as we want to, we absolutely want to. And when we get to the geometry proofs, you're going to see that there's a price to be paid when that happens. But then you get into contextual situations, and those are easier to come up with the conclusion, but you still have to justify the conclusion. Easier because if you have any kind of logical reasoning ability, and most of us do, because honestly, you have to have at least some logical reasoning ability in order to function as a human being. Right? So yeah, everybody has some. It's just a question of whether you use it consistently. Right? But if you think about these situations, in most cases, it's going to be like, oh, of course, this is the result. I don't know how to justify it, but at least I know what I'm supposed to get. Right? F represents I eat the right foods. S represents I get sick. So if I eat the right foods, so that's F, then I don't get sick. Well, I get sick is S. We're saying I don't get sick, so that would be not S. I don't get sick. Or I don't eat the right foods. So not F. So we want to prove that they're logically equivalent to one another, right? But this is the same thing as the implication identity. It's just we're using F's and not S's. Honestly, I think the implication identity, actually a lot of these are kind of, I'll say they're easier to see the relationship if the question you're being asked doesn't have P's and Q's in it, right? Because like I said here, the implication identity, I'll just do a little copy paste job. I keep hitting add a comment. They changed it on me, and now I'm hitting the wrong thing. Right. So I have the implication identity, which tells me P implies Q is equivalent, logically equivalent to not P or Q. So instead of having P implies Q, I have F implies not S. Right. So F is taking on the role of P. Right. So follow it through logically. If P gets negated in the implication identity, then F should get negated in the implication identity. Right. Not S is taking on the role of Q. Q remains the same in the implication identity. So therefore, not S should remain the same in the implication identity. All right. So now we have almost the correct final answer. We just have to justify how it becomes I don't get sick or I don't eat the right foods. All right. So by the commutative law, not F or not S is the same thing as not S or not F. And again, that's the commutative. All right, so we have implication.
Professor, Professor, I can't see what you're writing.
Oh.
Oh, thank you.
Oh, okay, no problem. Yeah, so it's just a matter of swapping the order to make it equivalent to what they're asking us to make it equivalent to. All right. So it logically follows from if I eat the right foods, then I don't get sick, that I don't get sick or I don't eat the right foods. Right? But our job is to justify the connection, the chain of custody. No, it's not that complicated. But the logical reasoning that gets you there. All right. M represents Michael likes math. S represents Michael likes science. All right. So same idea. I like the highlighter. It helps me keep things organized. Yeah, Michael likes math. It is not true. Yeah, this is that parentheses thing that we were talking about before. It is not true that Michael likes both math and science. All right. So we got likes math, likes science. So they're saying it's not true that Michael likes both math and science. Right? The issue with this one is nobody speaks out. And in fact, people are more inclined to speak the way the second sentence is represented. Michael does not like math or Michael does not like science, but even people aren't going to speak that way either. They're probably going to say something like, Michael doesn't like math or science. Right? But then it's a question of, well, which one does the not like part apply to? I mean, contextually, it would make sense that it applies to both, but there's always that gray area. Right? So Michael does not like math. Michael does not like science. So not M or not S. This one's actually a pretty nice, easy one, right? Because we have the Morgan's laws. Which says that if you have not P and Q, that's equivalent to not P or not Q. So here it's just a straight swap because I have not M and S. So M is taking on the role of P. So what happens to P? P becomes not P. So M would become not M. S takes on the role of Q. What happens to Q? Q becomes not Q. So S would become not S. All right, and that just happens to be what we were looking for. So in a straight run by De Morgan's laws, we're able to prove. All right, so let's take another 5-minute break, maybe 4-minute break. But then we'll come back and we'll just kind of put a ribbon on it all. We're pretty much done. I got a couple examples here that I know are a little too much, and there's some that are just right. So let me I'll finish up with those.
Can I just, so are you saying that both are Are we giving a reason they're not, or we're saying for number 4? What's the conclusion on that one?
Oh, that was De Morgan's laws.
Okay, so that's meaning that that it is, right?
Yeah, correct. Yeah, we didn't have to do anything beyond making a substitution into De Morgan's law.
Okay, and so that means that when it says prove they're logically equivalent or give a reason why they're not, by doing De Morgan's laws, you've proved that they are logically equivalent.
Correct.
Okay.
So just a couple more, it seems like a lot, but these contextual examples are a little much. So we're going to just kind of hop on down to the symbolic ones, which seem pretty crazy, but what they are, once you get over the shock of the appearance of them, is completed proofs that we just need to justify. Right? So it's not as bad as it seems, at least hopefully. That's the plan. So let's just. So when I say that something is a premise, that's another way of saying it's a given statement, right? So it's something that we know to be true, right? This is like Sam Darnold. If he does not get injured, then he will throw for 4,000 yards. If he throws for 4,000 yards, then they will win the Super Bowl. These are all the assumptions that we're making, right? So what's happening here is conclusions are being drawn from this set of premises. It's just a question of what conclusions there are, right? So taking a look at, for example, number 2 and number 3, the premise 2 and premise 3, and the reason why I'm focusing on those is because you see a not G as my first conclusion in number 4. It looks like that's drawn from the relationship or relationships that exist in 2 and 3, right? Now, modus ponens tells us that if you have P implies Q and also a P, that's the affirms by affirming, then the result is going to be, it's basically the law of detachment. Like we're affirming the premise, so the conclusion would be true. Right? So that's like saying, if I do my homework, then I will pass the test. I did my homework, so what would you expect to happen? You'd expect to pass the test, right? So this one's a little bit more complicated, but it's saying, taking on the role of P is S or L, right? Taking on the role of Q is a not G. Right? If we combine that, we take these two premises and put them together, we combine that with a not, I'm sorry, with an S or L, we would be affirming by affirming, affirm by affirming, right? We're saying S or L, if S or L is true, then so is not G. Well, S or L is true, so then therefore so is not G. Right? So that would be a logical conclusion, not G as a result. Right? So that would be my bimodus ponens. Now you wouldn't have to show any of this work here. I'm just doing that to explain why it all plays out the way it does. But as long as you come up with the modus ponens, you're fine. Now, we have a standalone not G. If you compare that with the first premise, you see it's the same structure, right? It's still affirm by affirming, because I have a not G implies all this other stuff, and I'm now confirming that the not G is a true statement. So that's following logically that all that other stuff would also be true. Right? Also by mode exponents. And so all that other stuff, all of this other stuff would be true, and that's what we have in 5, so also true by mode exponents. Right? The next justification is something that we haven't actually seen. Let me see if I can paste in my list again. Nope. It's the law of disjunctive inference, but let me go back and get the list again, just so I have something to point to. I guess it really doesn't matter where I put it because all these other problems are irrelevant now. Let's get rid of this stuff. All right. So the one that applies here is the law of disjunctive inference. I'll just highlight that. That's number 15. Right. And that one, I mean, hopefully when you reason things out, it starts to make a little bit more sense. But if there is it's an acquired taste, and there is a learning curve, but some of them make more sense than others. Disjunctive inference. Right. So the way this one works is if you have an or statement and you can eliminate one of the components of the or statement, then the other one must be true. Right? There's 2 variations on this. It's really 15 or 16. But basically, in just normal parlance, it would be, I am wearing a red shirt or blue shorts. I'm not wearing a red shirt. Okay, so you're wearing the blue shorts. That's what's happening there. Right? So if I tell you that I have P or Q, but then I tell you right after that that it's not P, then we can conclude that it must be Q. That's the law of disjunctive inference. There were one variation of it, because I could have also said P or Q, but it's not Q, so therefore it would be P. Right? So there's different possibilities. But in this case, if I look at my conclusion in 5 and compare it with 4, you see I have G or S implies G. All right, so G is taking on the role of P, and S implies G is taking on the role of Q. Right? So then if I tell you that G is not true because not G is true, then that's basically telling us that this is out, right? Because this is a contradiction, right? If I'm telling you that this is the true statement, then its opposite must be false. So that tells me as a conclusion, if it's a choice between the two, if it's G or the S implies G, well, it can't be the G, so it must be the S implies G. All right, and so that's law of disjunctive inference in my sideways arrow. All right, so law of disjunctive inference. I just abbreviated the living daylights out of that. Okay, so it's easier said than done because it's like, oh, this is, all we got to do is write the the reason for the conclusion. Yeah, you still got to write the, come up with the reasons. It's got to make sense, right? So then somehow we come up with a not S as a conclusion. So it's got to be like, all right, well, how do we know that? Well, that one's going to be a little easier because if I take, let me just shrink this down and move some things around here. Okay, let me do it this way. Let's sum this up a little bit. All right, so we know that not G is a true statement. We also know S implies G is a true statement. So we have modus tollens, which tells us that if you have P implies Q and not Q, then that's going to be equivalent to not P. Okay, so here I have S implies G and a not G. I wrote a Q for some reason. Who knows why? It's the same structure, right? S is taking on the role of P. G is taking on the role of Q. So the result here is going to be not S. Right? So that's modus tollens. That's our justification. So then we have the one premise that we haven't really done much with yet. I mean, we did a little bit with it, but that's the third premise there. S imply or S for L. That's another law of disjunctive inference between, well, actually, no, yeah, it is, because we have S or L. And then we also have a not S. Right? So that follows the same mold as the law of disjunctive inference. This guy over here, because I'm basically saying I'm wearing a red shirt or blue shorts. Oh, and by the way, I'm not wearing the red shirt. So, okay, so you're wearing the blue shorts. Right? So it's the same idea, but this would be logically equivalent to L. Right? Because it's basically like this is canceling with that. So law of disjunctive inference would be the justification for that. The next example, for some reason, is an exact duplication of the one we just did. That's good news or bad news, depending on how you look at things. But again, it's just they're laws. It's referencing laws. If you can find the appropriate rule that makes sense under the given circumstance, and everything's going to kind of come together, the longer it takes you to do it, the more difficult it'll be, obviously. But you'll get there. It's just a matter of having access to that list. And you'll have access to that list because everything in this course is going to be open notes. Right? So you don't really have to worry about that. Sorry. So the last one, justify each step in the following proof. Same deal. You look at the different components, and it's really the standalone things that are going to kind of help you make the conclusions. Right? So you have that not D. That not D is something that you could rely on to be true. Right? When they tell you it's a premise, we're saying assume that that's a true statement. just go with it. So if I take that D or not A, and combine that with the not D, I think about what kind of conclusion I can get from that. If I tell you it's this or that, it's not this, so it must be that. Right? And so that's what's happening here. The conclusion for this would be not A, it's just the question of what justifies that. Right? So that would be our law of disjunctive inference. All right. So that doesn't give us a justification for number 5, but it does give us a justification for number 6. All right. But maybe we could use that conclusion to help us draw a conclusion about something else. All right. So I see I got a not A that I can work with. Right. And I see that the first premise here has a not A in it. So not A, then B implies not C. I want to combine that with a not A and draw a conclusion from that. And it's just a question of, well, aside from what the conclusion would be, I would want to know what the justification would be for that conclusion. All right. So what I'm doing here is I'm affirming my premise. My premise is not A, and I'm affirming that, or we could say confirming. So the result would be B implies not C. So if they have that written down in the list there, I'm good to go. The rationale, when we affirm by affirming, when we confirm the premise of a conclusion of a conditional, that's the modus ponens. All right, so that's justification for number 7. So we still haven't justified the not B, but we do it in the order that makes sense. Right. So far I've used, and it doesn't mean I can't use a premise more than once, but generally, if you've used it once, you're probably not going to use it too many times after that. I've used the premise number 3. Right. I didn't highlight it, but I used that along with not D with the disjunctive inference. I used conclusion not A along with the first premise. So now it's a question of, okay, there's something else I can do. Well, I do see that there is a not D in my second premise. Right? I've used the not D in the law of disjunctive inference, but that doesn't mean I can't use it again. Right? So if I'm looking at the not D implies not C then A, and I'm putting that together with the not D, right? That's going to be the same idea. It's the modus ponens. Right? It follows the same mold. Right? So looking at the structure, there's no reason to think that we would get anything else, right? Than what we would get in any other circumstance when we use modus ponens. Whatever the conclusion is of the condition. So not C then A. Again, modus ponens. All right, so that gives us 8. All right, so again, we're just kind of looking around to see if there's anything else that we can determine in terms of a conclusion. Now we want to start, we've used all the premises, some of them more than once. Now I want to start looking within my conclusions to see if I can draw anything beyond what's already presented there. Now, there's one here, and this is a rule that we haven't talked about at all yet, but it's a good one because it's kind of in the realm of common sense. So if I tell you that you have P implies Q and Q implies R, then that's equivalent to saying P implies R. All right, that's the law of syllogisms. All right. If I study, then I will pass the test. If I pass the test, I will get an A in the course. Therefore, if I study, then I will get an A in the course. Makes sense. All right. So B implies not C, not C implies A, so therefore B implies A. Right? It's basically saying, right, cut out the middleman. Why not just go from the B to the A in one shot? Right? So that's the law of syllogisms. Some people call that the chain rule. That's not really a good name for it. Right? So there's only one conclusion. Oh, actually two conclusions left. Somewhere along the lines, we're going to have to get a not B. I don't see where. I think. Let me just double check something real quick. That might be the last and final typo in the entire sheet. That actually might have been a premise. No, actually it has to be a mistake. There's no way that could be correct. Right? That shouldn't be there because we have a not be down here, and that's what we're ultimately going for. So it can't be a premise because that's got to be the conclusion. That never should have been there. All right. So the last and final would be taking 6 and 9 and putting them together. All right. So that would be, so looking at B implies A and not A, that would result in a not B. And that's modus tollens. Yeah, so pretty funky stuff.